Hello and welcome back. So this video is for class 12 and we will continue with alternating current. So in the previous class we saw a derivation for a purely inductive circuit. So when you connect an AC power supply to an inductor only, we found out what is the relationship for the voltage and the current, and we found that the current lags behind the voltage by pi by 2, correct? So the phase difference is pi by 2. Today we are going to find a formula for the average power dissipated. Now I am sure you remember that when we did it for the a purely resistive circuit, we found that there is some power being dissipated. So let us test that in an inductive circuit whether we get any power. The formula that we use here is this one, that is power is equal to voltage into current. Here we cannot use I square R. Reason being that there is no resistor connected, correct? We only have a inductor. So therefore we will use P is equal to VI. That is the formula we will use. So let us see the derivation. So we will write power is equal to small v into small I. That is the alternating voltage into alternating current. So this is the instantaneous power that we are getting. How much this will be? So P will be equal to V, we know is equal to Vm sin omega t multiplied by how much is I? I is Im sin omega t minus pi by 2. This is the relation that we have already derived. So okay, no need of repeating it. Now we are going to modify this relation for our convenience. So what we'll do, we'll use the identity that sin of omega t minus pi by 2 is nothing but cos of omega t. Okay, so what we get, therefore P is equal to minus Vm. Of course, sin of omega t minus pi by 2 is minus cos of omega t. So we'll get P is equal to minus Vm. Vm, this will be as it is, sin omega t, and this term will become Im cos of omega t. As we said, sin omega t minus pi by 2 is minus cos omega t. Fine. Then again let us rearrange. This will write as minus Vm Im sin omega t cos omega t. Then we'll use the identity that sin theta cos theta is equal to sin of 2 theta by 2. Therefore we will get this as minus Vm Im sin of, so 2 omega t, that is 2 theta, so that is sin of 2 omega t, this thing divided by 2. This is the instantaneous power that we are getting. Now we want to find the average power, so we will take the average of this entire expression. Okay, so now when we take the average, what we will get? Minus Vm, Im and 2 these being constants will come out, so we will need only the average of sin of 2 omega t, and the average value of sin of 2 omega t is 0. Basically the average value of any sine function is always 0. Again I'll give you a simple explanation for it, just like before. Let us say sine of theta. What is the maximum value you can get for sine of theta? 1. What is the minimum value you can get for sine of theta? Minus 1. So all the sine values, they keep alternating between plus 1, minus 1, plus 1, minus 1. So over a complete cycle, whatever is the number of plus 1, same is the number of minus 1. So basically what happens is total comes to 0. So average of this sine 2 omega t will be 0, and therefore the average power that is dissipated in the circuit will be equal to 0. So in a purely inductive circuit, the average power we get is 0. Okay, so that is the derivation. Next we are going to find a relationship for a purely capacitive circuit. So what we do, we'll take an AC supply connected to a capacitor having capacitance C. So you will see all these derivations will be very much similar. How we did it for the resistor, similarly we did for the inductor, and similarly we'll be doing it for the capacitor. So you are going to see the style of steps is going to be very much similar with some minor changes. Okay, and I'm sure if you read it just 2 times, the entire concept you will understand very easily. Okay, so let us use Kirchhoff's loop rule for this. We know voltage across the power supply equal to voltage across the capacitor. How much is voltage across capacitor is equal to V is equal to Q by C. So therefore we will get the AC supply V is equal to Q upon C. Q is the charge on the capacitor, C is the capacitance. Fine. But we know how much is V? This V is equal to Vm sin omega t. This is equal to Q by C. Therefore, you can say Q, the charge, is equal to C into Vm into sin omega t. Okay. Then how do you find out the current? We can find out the current I taking dq by dt. Correct? That is what current is, rate of charge per unit time. So I is equal to dq by dt. From this relation you get q. So we get this as the derivative of capital C Vm sin of omega t. Fine till here. Then what do we know? C and Vm are constant, so it is only derivative of sin of omega t. What is derivative of sin omega t? Derivative of sin omega t is omega cos omega t. So what we will get, therefore, I is equal to omega C Vm cos omega t. Fine till here. Then we will use the identity that cos omega t is nothing but sine, that is sine cos theta is equal to sine theta plus pi by 2. So therefore we will get cos omega t as sine omega t plus pi by 2. Therefore I will get omega c Vm sine of omega t plus pi by 2. Okay, so this expression gives a value for the current. What you will notice here is that the current is leading the voltage by pi by 2. In the case of an inductive circuit, we saw this value as minus pi by 2. So current was lagging behind by pi by 2. But here in a capacitive circuit, the current leads by pi by 2. Fine, that is something to be remembered. So now what we will do, we notice that this quantity omega c Vm is nothing but the peak current. So this we will write as peak current Im. So therefore we get I is equal to Im sin omega t plus pi by 2. Fine. Then what we saw, how much is Im? Im is omega c into Vm. Let us write this as Vm upon 1 by omega c. Now there is a specific reason why we have written this omega c like this. Okay, what we are going to do, this factor 1 by omega c we are going to call as the capacitive reactance. So therefore we will get Im is equal to Vm upon Xc. What is Xc? Xc is 1 upon omega c. This is similar to XL, that was inductive reactance. This is Xc, that is capacitive reactance. So, and what you are noticing, Xc is 1 upon omega c. Once again, capacitive reactance is similar to resistance. It has the same unit, that is ohm. Okay, SI unit of inductive capacitive reactance is ohm. It does the same work as that of resistance in a capacitive circuit. Next, let us find the average power dissipated in the capacitive circuit. Once again we will write power will be equal to Vi, which will be equal to Vm sin omega t. And how much is I? I is Im sin omega t plus pi by 2. Okay. Now again we'll make a change. We'll write sine of omega t plus pi by 2 as cos of omega t. Okay, using this previous identity. So therefore we'll get T is equal to Vm sin omega t Im cos omega t. And once again we will use that sin omega t cos omega t is nothing but sine of 2 omega t by 2. This is the same equation, that is sin theta cos theta is equal to sine of 2 theta by 2. So again what you will get? You will get therefore the instantaneous power as Vm Im sine of 2 omega t by 2. This is the instantaneous power. How much will be the average power? Average power will be the average of this entire expression. And as we discussed previously, the average of sine of 2 omega t will be 0. So the average power dissipated in capacitive circuit will also be 0. Okay. So these are the two things you have to remember. That is, average power dissipated in capacitive circuit is 0, as well as inductive circuit is also 0. Okay. But this was not the case in a resistive circuit. In resistive circuit, we did get some power dissipated. Okay. these kind of derivations, these are asked in the exam. Okay, so it is important that we understand them properly. Next, we are going to see relations for a series LCR circuit. What is a series LCR circuit? We will have an inductor L, capacitor C and resistor R. These three connected in series with an AC power supply. That is called as an LCR circuit. Okay, simple to understand. Then what is the relationship you will get for an LCR circuit? Voltage drop across all these three will be equal to voltage drop across the power supply. So therefore we will get, how much is voltage drop here? L di by dt, Faraday's law, plus how much is voltage drop here? Q by C, plus how much is voltage drop over here? I into R. This will be equal to the voltage drop across our power supply. Okay, so that is the relationship for an LCR circuit. But of course, this will not help us to find out the instantaneous and the maximum current. So what we are going to do? We are going to use the Phasor diagram to derive that relation. So now what I am going to do? I am going to erase this diagram. But remember, we are basically talking about the LCR circuit only. Okay, so let us make a Phasor diagram for our LCR circuit. Here we will use some phasors, vectors. Which are the vectors we will use? We will use the vector capital V for the power supply. We will use the phasor VL for the voltage across inductor. Then VC for voltage across capacitor, and VR for voltage across the resistor. And we will use the phasor capital I as the current phasor. Okay, current will be only one phasor. Why? Series circuit. So same amount of current will go through all three, right? But voltages for all the three will be different. So we will have separate phasors for inductor, capacitor and resistor. Okay. Then we know when we want to make a phasor diagram, we draw these coordinates like this. Fine. Now we know that the current in a resistor is in the same phase. So we know that VR and I, they will be in the same phase, correct? So let us draw them first. So here I will draw the current phasor I, and in phase will be the voltage, the resistive phasor, correct? So you see that I and VR are in the same phase, so they are parallel to each other. Okay, they are actually coinciding. Then what do we know about VC? We know that the capacitive voltage is actually behind, that is current is pi by 2 ahead of the capacitive voltage. So with regards to I, the capacitive voltage will be 90 degrees here like this. So this will be VC. Okay, so if I make VC here, then I see that 90 degrees, that is where the current is. Current is leading by 90 degrees, correct? Where will be the VL, that is inductive voltage? Inductive voltage will be like this. Okay, this will be VL. Here you see that current is pi by 2 behind the VL. Okay, in inductive voltage, we saw inductive voltage mein the current was behind the voltage, correct, by pi by 2. And of course, you can see that VL and VC, they are making they are 180 degrees with respect to each other. So they are actually along the same line in opposite directions. Okay, this relation is very important to understand because the entire derivation will depend upon this. So once again, I and V are in the same direction. VC pi by 2 behind I and VL pi by 2 ahead of I. Okay, so this relation needs to be understood, and this phasor diagram you will have to draw in the exam if this question is asked. Now here is what I want you to notice. VC and VL, they are 180 degree to each other. So basically you can imagine that these two vectors are actually one single vector. Okay, one single vector, that is VC plus VL. Fine. But since they are opposite to each other, the combined magnitude is going to be a subtraction. So we will say that the magnitude of VC plus VL is equal to, let us put a modulus for this, is equal to VCM minus VLM. CM, that is the peak voltage for the capacitor, and LM, peak voltage for the inductor. So magnitude of VC plus VL is going to be VCM minus VLM. Okay, now remember this. Now I am going to replace this phasor diagram by a diagram which will help us to find out the relation. Okay, so now what I will do is, let us make one vector, that is VRM. What is VRM? VRM, that is nothing but the maximum, the peak voltage for the resistance. And here we will have the combined vector, okay, which is having a magnitude of VCM minus VLM. Okay, these two vectors combine, okay, and their output is what? Their output is actually the vector, that is the input AC voltage. Okay, so that vector will get here. So we'll get this. Okay, and this is nothing but the peak voltage that is actually provided. Okay, is this making sense? So what we are getting? These two vectors combined will give Vm. Okay, that is the input voltage. Now we can use the Pythagoras theorem for it, right? Using Pythagoras theorem, what we can write? Vm square will be equal to Vrm square plus this side square, that is Vcm minus Vlm square. Let us do that. So using Pythagoras theorem, we will get Vm square is equal to Vrm square plus Vcm minus Vlm bracket square. Note this relation. I am going to continue it here now, right? So what we will get now? Therefore, Vm square is equal to, now how much is Vrm? That is voltage across the resistor. We already know that is equal to I into capital R square, correct? Plus, how much is Vcm? Vcm will be equal to I into xc square minus how much? Ixc. How much is Vlm? That is equal to Ixl and this bracket square. Okay, I hope this is not you're not finding this to be too difficult. Okay, we are using the same relations that we did in the previous way. We know that the voltage is equal to current into resistance. So for Vcm, that is for the capacitive voltage, it will be the current into the capacitive reactance, and for the inductance it will be current into the inductive reactance. Just one change, this will be Im, the peak current over here. So we will get IMR bracket square plus IMXC minus IMXL whole bracket square. Now let us make some more changes. We see that Im square is common in all. So let us take Im square outside the bracket. So we'll get Im square outside. And what do we get in the bracket? In the bracket we get capital R square plus XC minus XL square. So this is the relation we are getting. Vm square is equal to Im square in bracket R square plus XC minus XL square. Or you can write therefore Im is equal to, right, you can transfer this entire expression in the denominator and then take the under root. So Im will be equal to Vm upon under root of R square plus XC minus XL square. Okay, now this term that we are getting, under root R square plus XC minus XL square, is known as the impedance. Okay, impedance is basically the effective resistance of an LCR circuit. Okay, this is written as capital Z, and we get that capital Z is equal to under root of R square plus XC minus XL square. Okay, from exam point of view, this is an important concept of impedance. Okay, so see, if you are having a resistor circuit, we are having resistance. If you are having a capacitive circuit, we are having capacitive reactance. If you are having an inductive circuit, we are having a inductive reactance. But if you are having all three, LCR, in LCR you get the impedance. Impedance has the same unit as that of resistance, that is ohm. Okay, and what is the formula for impedance? Formula for impedance is under root of R square plus XC minus XL. Okay, again a very important concept. Make sure that you understand this thoroughly.